Have you ever just stopped and wondered how your phone actually understands what you're saying, or how a chatbot can hold a conversation that feels, almost human? Well, today we're going to pull back the curtain on that AI magic. We're diving deep into how we teach a machine to understand our language one word at a time. So take a look at this sentence. For us, it's pretty straightforward, right? We know what it means. But for a computer, this is basically gibberish. It's just a collection of pixels on a screen. So how in the world do we get a machine to grasp the meaning behind these words? That's the exact puzzle we're going to solve together today. All right, here's our game plan. We're going to tackle this in 5 key steps. First, we'll look at the fundamental language barrier between us and computers. Then, we'll see how we clean up our language to make it machine-friendly. After that, we'll build a custom dictionary for our AI, introduce a really clever trick called One-Hot Encoding, and finally, we'll talk about where this trick shines and where it falls a little flat.
Okay, first up, the language barrier. And this is really the heart of the whole challenge.
You have to remember, computers live in a world of numbers, zeros and ones. That's it. Our words, our language, it's all abstract and squishy to them. If you tell a computer the transformer is hot, it has no concept of hot. It doesn't feel temperature. It just sees a pattern of letters. So our very first job is to figure out how to translate our words into the only language it speaks, numbers. So where do we even begin with this translation process? Well, it starts with a little bit of spring cleaning. We have to pre-process our text, which is just a fancy way of saying we need to tidy up our messy human language so the machine doesn't get tripped up by all of its quirks. Look at these 2 sentences. To you and me, they're the same thing, but to a computer, they are completely 100% different. Why? Because one has a capital T, another word is in all caps, and there's an exclamation point. A computer sees transformer and transformer as 2 totally separate words. So we've got to standardize everything. And we do that with a simple 3-step pipeline. First up is tokenization. We just chop the sentence into its individual words, or tokens. Easy enough? Next, we force everything into lowercase. Now, transformer and transformer are finally the same thing. And last, we clean out all the junk, all the punctuation, the exclamation points, anything that isn't a core word. What we're left with is a super clean, predictable list of tokens ready for the real work. All right, our text is officially clean and tidy. Now what? Now we need to build a dictionary for our AI. Think of it as creating a master word list, the AI's entire known universe of language. So we take all of our cleaned up text, we find every single unique word, and we put them all into one big list, usually sorted alphabetically. This list is our vocabulary, and it is absolutely critical. It's the definitive guide. From this point on, every single word the AI knows is in this list, and each word has its own unique spot, or index. This vocabulary is the foundation for everything we're about to do. Okay, dictionary in hand. Now we face the million-dollar question. How do we assign a number to each word? And, more importantly, how do we do it in a way that doesn't accidentally mislead the AI? We can't just have it thinking that word number 50 is somehow bigger or more important than word number 20. A pretty logical first thought might be to do something simple, like every letter on a keyboard has a number behind it, right? An ASCII value. So why not just add up the values for the letters in a word? Seems intuitive, gives you a number for every word, but this idea has a huge, fatal flaw. And here's the problem. Look at the words eat and tea. Same letters, different order. If you sum up their ASCII values, you get the exact same number, 314. This is called a collision. The computer would see the number 314 and have absolutely no way of knowing if we meant eat or tea. To the machine, they'd be identical. And that's a deal breaker. We need a unique ID for every single word. So how do we get around this collision problem? With a really brilliant and surprisingly simple method called One-Hot Encoding. Here's the big idea. Instead of assigning each word a single number, we give it a whole list of numbers, a vector, that's made up almost entirely of zeros, except for a single one that acts like a beacon. So the formula is this. If our vocabulary, our dictionary, has, say, 18 words in it, then the vector for every single word will be 18 numbers long. And to represent a specific word, we just put one in the position that matches its spot in the dictionary, and leave everything else as a 0. That's it. Let's make this crystal clear. Remember our vocabulary with 18 words? Okay, the word transformer happens to be the 16th word in that alphabetically sorted list. So, to create its one-hot vector, we start with a list of 18 zeros. Then we go to the 16th position, and we just flip that 0 to a 1. Boom! That's its unique numerical fingerprint. No other word in our entire dictionary will have a 1 in that exact spot. So now, when we want the AI to read a sentence like transformer tripped, it doesn't get the letters. Instead, it gets a stream of these vectors. First, it sees the long vector for transformer, with the 1 in the 16th spot, followed immediately by the unique vector for tripped. It's a sequence of these numerical fingerprints, fed to the AI one after the other.
Now, one-hot encoding is a powerful, foundational concept in this field. It really is. But it's not the final answer. It's got some amazing strengths, but it's also got some pretty serious weaknesses we need to talk about.
On the plus side, it's dead simple. You get it, I get it, it's easy to implement. And crucially, it doesn't create those weird artificial relationships. The AI won't think word 2 is somehow twice as important as word 1. Every word is on equal footing. Plus, it creates a standard fixed-length input for our models, which they absolutely love. But here's the catch. If your vocabulary is huge, say 50,000 words, then every single vector is 50,000 numbers long. That's massive and incredibly inefficient. It's mostly just empty space. The bigger problem, though, is that it has zero understanding of meaning. To a one-hot encoded model, the words car and automobile are as different as car and planet. They are complete strangers. And finally, it's totally blind to context. Apple, the company, and Apple, the fruit, get the exact same vector.
And that leads us to the final, really important question. One-hot encoding is fantastic at making sure every word is its own unique island. But language isn't about islands. It's about the bridges between them. It's all about relationships. So if this method makes every word totally distinct, how can we ever teach an AI that king is related to queen, or that walking is similar to running? That challenge, well, that's the next giant leap in this journey.